on the very first lecture, I mentioned the difference between electrical devices and the electronic devices. Electronic devices focus on working with data and information.
Data.
Yes. And electrical devices are mainly for energy conservation. And this data representation in the electronic circuits can take two different forms. They can be either analog signals or digital signals. The main difference between analog and digital is the voltage levels. We already discussed this on the very first day. In analog, you can have a range, and within that range, any value is valid. But in digital signals, you don't have ranges, you have some fixed levels. So you can only have those voltage levels, nothing in between. Now, if I went a little bit abroad, syllabus, you do have something called tolerances, right? Not ranges, tolerances. That also make it
Like the maximum voltage one can bear. Is it something like that?
not exactly.
Okay.
Now let me explain it. So then you can see the advantage of the digital electronics and how it can tolerate certain noises. Now let's say we have some kind of sensor or a circuit, and we have another circuit here. You are sending a signal from here to here. Now, of course, you have grounds and everything. I'm just showing the data line. Assume this is an analog circuit, and this is again an analog circuit. And let's say you have a voltage range for these two circuits. It could be, let's say, 0 to 10 volts. So your original signal generated from here can be something like this. Okay. And let's say, due to some problems with interference and noises and all the other things, there are some small noise adding up like this. So this is the original signal, this is the noise. So the person at here might, let me just do something a bit different. Let's say some kind of sinusoidal noise. Let's say 50 Hz hum. So the person who's getting here will get a small different signal than the original one. Something, maybe something like this. So this is the original signal. This is, we'll call it as the source. And this is the destination. So the person who's getting this signal do not have a way to remove this particular noise. Why? Any value here can be the actual value. If he doesn't know the original, if he doesn't know the noise, shape of the noise or anything, he cannot remove the noise. Because anything here will be a valid signal. Now we'll try to do the same thing, but let's say we are using a digital circuit. And digital signals have only fixed voltages. So let's say we have 0 volts and 5 volts. Only these two levels are valid. So the original signal will be something like this. See, something like this. And again, you get, let's say, some kind of noise. So your final output will be original signal plus the noise. So it will be something like this. Right? But the receiver knows either the signal should be at this voltage level or at this voltage level. Because it's a digital signal, it should be only 0 volts or 5 volts. So that means this particular signal is most probably, what do you think about this signal? There can be only two choices. It can be either a 5 volt or a 0 volt. What do you think this line is?
5 volts.
5 volts. This will be 0 volt.
0.
He's not going to assume this. Let's say this is 5.1 and this is 4.9. He is not going to assume 4.9 is the actual signal sent by the source. Why? Because it's a digital signal. So 4.9 means he sent 5 volts and somewhere in the middle something happened. It got corrupted. Some kind of noise was added. So now he know the original signal should be 5 and there was a 0.1 volt noise added somewhere. So he retrieved the original signal. For the processing, he will retrieve the original signal. So as long as this signal then is larger than the noise, it can automatically recover the original signal. Is it clear?
Yes, sir.
So that is a very big advantage in digital electronics. So I mentioned you how it can help you reduce the noises. Right? In the analog case, you couldn't do it because in the analog case, if you had the signal like this, a noise like this, the final output again can be a valid signal. Maybe this is the original signal the sender has sent. Maybe it's a different one with the noise, but we do not have a way of validating it. The reason is any value within this range is a valid one. But here we know what should be sent, what should we see. So anything deviating, we should consider it as a noise. So now you might think, okay, recovering this.
Digital is quite convenient when it comes to circuits.
Yes, designing is also easy. How
Yeah.
they do it? Now, it doesn't actually have a much complicated circuit for this one. Only thing is, although we roughly say 0 is 0 volts, 1 is 5 volt. Now this is again a convention, okay? There are certain electronics working at 3.3 volts, certain circuits work with 5 volt, certain logic levels work with plus 12 and minus 12 as 0 and 1. And in microprocessors, they use around 1.8 volts. But for the most of the common ICs you find in market, it's in this convention. Usually 0 volt means 0, 5 volt means 1. Right? But in reality, this is actually a range. Something between, let's say, 0 to 1 volt might be considered as digital 0 by the IC. And this might actually be a range, something like 4.5 to 5.3 or something like this. These values I just picked from my head. I can't remember the exact values. So this is the tolerance range I mentioned. So even if you add a small noise, let's say your voltage drop to 4.6, it doesn't matter as long as it is within this range. Inside the circuit, it will be treated as a logic 1. It will be treated as a logic 1. So in the ideal case, you will have only two voltage levels, 0 and 5. Okay. And this gives you a very big advantage when it comes to computers and doing complex mathematical things. Why? Let's say something like this. When we are doing mathematics, we are actually doing some abstract numbers, right? When you say 1 plus 5 is equal to 6, 1 and 5 and 6 and addition, all these things are just concepts. They are abstracts. Right? So when you are doing an abstract kind of thing that is well defined, and when the thing is well defined, you don't have any noises. When 1 plus 5, you don't say 6.1 or close to 6 or something similar to 5.9 and a little bit bigger than 5.9. You don't see that. You exactly know the output should be 6 because it's a concept.
Yes.
Similarly, let's say you try to do addition by doing some physical kind of addition. You have one single block. No, let's say you have some kind of piece of stick, 1 centimeter long. You have another piece of stick, 5 centimeters long. So instead of adding it as an abstract concept, you try to put these two sticks together and measure the full length to get the result. So in that case, it may be 6 centimeters, or due to the physical kind of imperfections, it might be actually 5.99. Right? You got it?
Yes. This is quite complicated, no? So we can use digital here. Is it?
Yeah. So what I'm trying to say is, when you are doing analog electronics, you don't do the abstract. You're actually doing some physical calculation similar to this one. For example, if you want to add two numbers in analog circuits, there's a component that you can use. Do you know the component? Or let's say you want to subtract two numbers. There's an analog electronic component that you can use. Do you know what this is?
Gate, sir.
Not the gate.
This is diode. No.
Not a diode. This is an op amp.
Ah, open.
Right? So the way op amp works is its output is given by open voltage gain times non-inverting input minus inverting input. You can adjust this gain by using a feedback circuit. Let's say you adjust it to 1. So what do you end up with? V plus minus V minus. So in an analog circuit, let's say I want to subtract 5 from 3. What I can do is I can give 5 volts to here, 3 volts to here, assuming the gain is equal to 1. My output should ideally be, what is the value?
2.
2 volts. But remember, this is not a digital component. It is not trying to abstract. So if for some reason, if it became 5.1, or for some reason this op amp is get a little bit heated, so the gain is 1.01. Then what's going to happen? Your value will be a little bit different. It might be 2.01. And 2.01 is a perfectly good answer. We don't know whether it's correct or not. For example, instead of saying 5, if I had given 5.01, I will get 2.01. In analog world, 5.01 is a valid signal. So when you say 2.01, we don't know whether it is correct or not, unless you know the original one and you have done it manually. So if you are doing the calculation manually, there's no need for a digital computer. So in a case of analog circuit, let's say you have several large circuits like this. There are several op amps, some other amplifiers and things like that, all feeding into each other. So if you have a small error here, it will propagate to this one. Maybe there's a multiply, so it might be multiplied by 10. So you get an error of 0.1. Then you do a subtraction. Let's say the value from here is 0.2 and you have a subtracting it from here. Then you end up with 0.1. Originally, in the ideal case, if you don't have this noise, you might need to get 0.2, but now you are getting 0.1. The reason is any error you get in an analog circuit will propagate through it. It doesn't have a way of correcting itself. It doesn't have a way of correcting itself. But in
digital they have.
They have, yes, exactly. So if you get 5.1 and 0.1, it will not just do something like this. It will either output 5 or 1. So the input for the next one is cleaner. So even if you get a small noise here, again, it will remove the noise and come up with a 0 or 1. It's basically converting whatever is voltages to abstract logic level, 0 and 1. So you can have a very complicated circuit without worrying about too much about, still have to worry too much about noises. In analog, it is very problematic, right? So that's the other main advantage. The first advantage is when you are transmitting signals, you can very easily remove the noise. Second advantage is you are actually working with abstract concepts. You have the physical component, but it works as an ideal component. Works as an ideal one, right? But in analog ones, you have certain issues. Right. Now let's go back to our PowerPoint. Now we will look at analog and digital signal that we had seen, logic gates, Boolean algebra, and some circuits, and bit of things. Are you yes.
Small clarification. So in analog circuit, if there's an error, that will propagate along the rest of the circuit, no? But in digital, it is auto-corrected.
Yes, but remember these are mostly the noises or external interference, right? If you make error when you are designing the circuit, then it will not automatically correct. For example, let's say you want to add two numbers, but you design the circuit such a way you subtract two numbers. Then the circuit will not automatically read your mind and correct itself. You expect to add it, but unfortunately it's giving you the wrong answer, subtracting. But that's not the fault of the digital electronics. That's the fault of your circuit design. So errors can still be there, but they will be mainly due to designing issues, not due to noise or interferences or power fluctuations, things like that. Okay. Do you know what this first logic gate is?
Yes, sir. AND gate.
AND gate. And what is this one?
Yeah, both has to be on.
Yes.
To get an answer.
Do you know the name of this table? You have a name for it. We call it a truth table.
Truth table, yes.
Yes.
Okay.
The truth table is a representation of all possible inputs, input combinations, and respective outputs. Right? So in case you have only two inputs, there are only four possible ways. Either both of them are low, or first one is low and second one is high, or the first one is high and second one is low, or both of them are high. Those are the only possible ways you can arrange two inputs. There's no other way. Then you put all this combination in a truth table, and for each of these input combination, you write the output. Right? So it's a way of representing the information of a digital logic. So in this case, we are just showing it for a single logic gate, but truth table can be written for complicated circuits as well. Only requirement is input and input combination should be there, all input combinations. And for each input, you should have a way to determine in the output.
If we have 3 input, it will be like 2 to the power 3, as in 8.
Exactly, it will be 8 inputs because there are 8 possible combinations. Although not necessary, there's a standard way of writing the truth table. You write it using the incrementing order of binary numbers. For example, yes. If you want to write 0, in binary you write 0 in 0, 0. Let's say 3. You write 1 in 0, 0, 1 because you are adding 1 to the previous number. If you add another one to this one, 1 plus 1 is 2, but you don't write 2 here. Instead, you write 1 and take 1 to the next binary point. Just like when you say 5 plus 5, you don't put here, you put 0 here, take 1 to here. The same scenario here. this is 2. You add another one here, you end up with 0, 1, 1,
The one.
0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So we usually write it in that order. That is the kind of like a standard one. So even in any exam or anywhere, if you ask to write the truth table, try to write it in this order. That will be very easy for everyone. Certain cases, in the next session, we will talk about combination of sequential ones. Sometimes your output may not be exactly 0 or a 1. There are some exceptions. In certain truth tables, you might see something like this. There might be excess in certain inputs. Let's say this is the inputs A and B. Output is Q. So X here means it doesn't matter whatever the input. B input doesn't matter. As long as A input is there, output will be this one. Here again the same scenario. X means it doesn't matter. So it's basically a short form of writing the same thing. So this single line can be set to as 0, 1 and 0, 0. Whatever this B input, whether it's 1 or 0, output will be 1. So rather than duplicating it 2 times, you just put the X. Right? This is something extra, okay? Similarly, here if you have 1 and X, that means you have 1 and 0 and 1 and 1. In both cases, output will be 1. So it doesn't actually matter what this input is, whether it is 0 or 1, you still end up with a 1.
So this is like all time switch again, eh? Like
It's called doesn't care condition.
yeah.
So if you have something like this, let's say.
Is it the gate's name? Doesn't care condition?
No, it doesn't have a gate. I'm talking about truth table. Let's say you have something like this. So 0, 0, 1, 1 is 0, 1, 0, X is 0. So you can put X1 here. Let's say you have some long truth table like this. Here you have one place with the X. Here. So that means for the previous cases, if you have 3 inputs A, B, C, and Q, if A is 0, B is 0, and C is 1, you get this output. If it is 0, 1, 0, you get this output. 0, 1, 1, you get this one. If it is 1 and 0, and whether C is 1 or 0, it doesn't matter, you will always get a 0.
Oh.
You got it?
But sir.
Yeah.
So but in this we have 1 also, we have 0 also. So how do we know that that is 0 only without 1?
Okay, let me try to simplify it using this AND gate, okay? Now don't get confused, this is something extra, okay? Now, do you know the truth table for the AND gate?
Yes, sir.
Okay, let's draw it. So if you are drawing the full truth table, it will be 0, 0, 0, 1, 1,
0, 1, 1, 0, 1, 1.
Right. If you are drawing the output, what should be the value here?
Only the last one will be 1. Others are all 0, 0, 0.
0, 1. So this is the full truth table, no issue. But you can do the same thing, something like this. You can say A, B, 0x, 0, 1, 1, 1.
Others are all will be 0, no?
Did you see what I did?
Yes, sir.
These two gates doesn't matter as long as A is 0. So you can say A is 0, B can only take 2 values, 0 or 1. So it doesn't matter whether B takes 0 or 1, output will always be 0. So rather than writing these two lines separately, you can reduce to one line.
Like that. Okay.
So it's the same truth table, okay? Nothing different, same truth table. The only purpose of using this is to make it smaller. And sometimes make it a little bit clear. Little bit clear because And now when you see this truth table, you know that output doesn't depend on B. If you want to change the output in this combination, only the output A actually matters. Right? But if you are asked to write a truth table for AND gate, write this one, okay? Not this one.
This is just your teaching, no?
This is something here, something extra. We go to this only at a later stage.
Okay.
And there's another extra one just for the sake. Some logic gates have 3 different states. They are called tri-state. I mentioned earlier, output will be 0 volts or 5 volts. There's another state called high impedance. Is a no high impedance. What does it mean? 0 means your output. If you have gate output, this will always be 0 volt. It will try to draw it to the 0 volt. So if you have 2 LEDs, let's say 2 LEDs like this. This is 5 volt. One LED here, another LED here. Let's say my output is 0. What's going to happen? This is always 0. This is 5 volt. So this LED will light up. Okay. Do you understand my circuit?
Yes, quite complicating.
Not complicated. Let me just show it again. Let's say you have some AND gate or something. You put a resistor and connect a, let's say, another LED. Okay, we'll connect one LED at a time. There should be a resistor. For the time being, there's a resistor here. Okay, 2. So when this is 0, output is logic 0. Let me say this is logic 0.
Yeah, then output is
What is 0? So this LED will not light up. Assume you have another LED here connected to 5 volt. So this is 0 and this is 5 volt. This LED will light up. How it is going to light up? Now the current is going to move from here into this logic IC.
So will it go like that or will it go directly?
Go directly like this.
Yeah.
So if I draw 2 LEDs, it can get a little bit complicated. So for the time being, I'm going to say something like this. We'll just connect to another LED.
Or we can connect the LED near the circuit, the AND gate. Then it will be okay. No?
Or we'll do something like this. We'll connect a voltmeter. That will be easy. Right? So now what's going to happen is when it is logic 0, this will be 0 volts. This will show 0 volts. When it is logic 1, this will be 5 volt. It will show 5 volt. In the high impedance state, what it basically does is it's kind of like disconnect this output. It is like a switch that is closed. So this voltmeter is disconnected. We don't know whatever the voltage it is going to show. Even if you have a small pull-up resistor, let's say 1 mega ohm pull-up resistor, it will show 5 volts. If you have 1 mega ohm pull-down resistor, it will show 0 volts. Because it is essentially disconnecting the output from other part of the circuit. You can think of it like this. Okay, I now remember. It's easy way to show it. Think of it output like this. 5 volt, 0 volt. In normal logic circuits, you are basically connecting either to here or to here. Okay? So you are either basically connecting 5 volt rail or to ground volt rail. So it can be either current is flowing from here like this to the output of the gate, or maybe you are drawing the current and into the gate and grounding it. Right? So depending on whether you have a LED connected or voltmeter or ammeter or something, you will still get a current. Got it?
Yes.
In the tri-state one, you have a small difference. The difference is, instead of this, you also have another switch like this. In normal operations, it is closed. So in the normal operations, if you have a logic out, you will have something like this. If you have logic 0, you will have an input like this. But if you can put it into the high impedance mode, the third mode I mentioned, then the switch will be open. Now what's going to happen? Now there won't be any current. You're basically disconnecting it from the 5-volt line and the 0-volt line.
There won't be any current.
Yes, this is important if you are trying to connect two logic gates directly. Okay, now we are moving out of our scope, right? So for the time being, you just need to know in certain ICs there will be certain things called high impedance where you will usually denote as Z. So it basically means your output is disconnected. So high impedance can only appear at the output stage, and doesn't care condition will only appear at the input stage. Because you can't say that I don't care about the output. That doesn't make any sense. But for the most of the logics, and especially within the syllabus, we will only have two voltage levels. That means 0 and 1. 0 will be represented by 0 volts. 0 volts. 1 will be 5 volts. I also mentioned there will be some tolerances. For the time being, for this case, you don't need to worry about tolerances either. We will assume ideal cases.
Okay.
So we learn about the truth table. There's another way you can represent this particular operation. I mentioned digital electronics is kind of like an abstract one, like mathematics. So we are basically working with logic. Logic is again an abstract concept. So the abstract concepts can be represented using different ways. So this is one way of representing the AND operation. And your truth table is another way of representing the same data. And there's a third way of representing the information, that is through the Boolean algebra. So A and B are the input, Q is the output. A, B, Q. Right? So this is the third way of representing. Both of them are equal. You can represent any logic circuit using truth tables or gates or Boolean expressions. And you are able to convert between them as well, because it's the same information. So we'll learn about that in this course. So the next, we'll look at the next gate. What is the second gate? O gate. And in the O gate, you can see
Either any output is there, we get the
exactly.
input is there, we get the.
Now in the AND case, let's say you have 3 inputs. Then what will happen to the output?
Sorry, sir?
If you have
we have
3
input, then we'll have 8 outputs.
Yes. When will it be true?
As long as we have either one as 1. Like
for the AND gate, I'm asking.
AND gate, sir?
Yes.
We'll have only one output, sir. That is when all 3 are plus. I mean, like 1.
1. Yes, exactly. In the AND gate, the generic expression is all the input should be 1.
Yeah.
So A into B into C into D into ... up to N.
Yes.
Similarly, for O gate, the general expression is A plus B plus C plus like that up to N inputs. If any of them are true, output will become true. The third one is the NOT gate. It has only 1 input. And the purpose of the NOT gate is to invert the logic. So if you have 0, output will be 1, and if you have 1, output will be 0. And it is written by A bar, sometimes you can have a and a hyphen, kind of like a comma. That's again sometimes written. Rather than putting a bar, sometimes you have this small, what do you call?
We have studied bars on top of it. Bar.
Yes. Sometimes you have that one, sometimes you have the small hyphen, something like this. Sometimes you write it as this one, like this.
Okay.
I think the reason is when you start typesetting it, putting a bar might be a little bit problematic. Putting a dot is easy. Putting a plus is easy. But putting this bar might not have been easy at the earlier times when you're having computers at the beginning or
So
maybe
they have
typewriters.
given the apostrophe.
Yeah, that might be the reason. But now
Okay.
sometimes we use that as well. And even when I'm typing, it's much easier to put this one rather than putting this bar.
Mm.
But both of them mean the same thing.
It's like A dash, A dash. Or,
Yeah.
like
Even okay. You might know this because this is quite familiar. Have you read about Venn diagrams and set theory?
yes, sir.
In Venn diagrams, if you want to have the inversion,
Yes,
you
yes.
put this
That
symbol.
dash. Yes, yes.
It's the same thing because it's again a different way of representing logics.
Mm.
You have the union and intersection and things like that. This is kind of
Yes.
like that. So in the mathematical representation, sometimes you get this one as well.
Yeah.
By connecting these, okay, not actually connecting, the way it is built is different, but the simple way of understanding is sometimes you can put a NOT gate in front of other gates to create a different type of gate. We put another name for them. For example, if you put a NOT in front of AND, it becomes NAND.
No.
We know it because you have a small circle at the output.
Mm.
In the original one, you don't have a circle here.
When
Here
you
you have
merge
circle.
it, it becomes circle.
Yeah. You can see the output here. Now it is written as Q A dot B bar. A dot B whole thing bar. Now, another important thing you have to know is A dot B bar is not equal to this.
Different.
Right?
Their input itself will become reverse now.
Yes. You
Yeah,
first you have
output
to
is
do this,
already reverse.
and then you have to do this operation.
Mm.
There's an order. For
Mm.
example, even in mathematics, if you say 5 plus 5 multiplied by 2, what do you get?
We get 15.
You get 15. Why? You have to
Because
do this
for
first
math. Yes.
and then this one.
Mm.
But if you do it in this order, let's put a parenthesis,
20.
then you get 20.
Oh.
You can see the same expression, but not the same expression. The way
Mm.
you are operating can have different results. So similarly, if you first take the AND operation and then take in the bar for the inversion, not operation is different. First take in the inversion and then take in the AND operation. Right? Order matters. Even in everyday life, if you are making fruit salad, peeling the mango and putting them into a thing is different than putting it into the salad and then trying to peeling it, right?
Yeah.
The same thing. So it is important when you are putting operations, make sure you put them in a clear and a proper manner. If you feel like you might forget this, and if you feel like putting this one separately, put a parenthesis. That will remind you this is the same thing. This is a single unit. First, you have to start with within the circuit, within the parenthesis, and only then you have to take the inversion or the not operation.
Okay.
That might help you in certain cases, especially if you are building the expressions. Right. Again, I am moving a little bit outside. So this is basically means you have something like this.
Mm.
This dot represent this one. Sometimes you get something like this. And this is not a standard logic gate. It doesn't have a special name. But what do you think this circuit actually equal to?
Now this one will be like output. If it is 1, it will be reversed as 0.
Not this one. I'm talking about this one.
Yes, it's a down on this I'm talking about. Now here the A bar dot B.
Yes, it will be same as putting this circuit.
Yes.
So when you have a dot, that means you are taking the NOT operation or the inversion. In certain ICs also you will see it. Sometimes you have inputs like this. Certain pins, you will have input like this. So this means it's actually doing the logics in a separate direction. What do you mean by that? Let's say this is a counter and let's say this is the reset pin. Usually the practice is when reset pin goes high or when someone presses the button, it will reset. But if you have this bar, not the bar, this little circle, that means it's the opposite way. That means if you go 0, then the circuit will reset. Something like that. In certain circuits, you will see.
As in, say, if you press reset, it won't get reset. But if you don't press reset, it will get reset. Is it?
Yeah. When I say press, I actually mean getting into the true value. Okay.
Okay.
So that's again a little bit extra, but you will probably find them in many data sheets. For example, let me show you a very common IC 4017. No, this circuit diagram doesn't show it. It actually has the logic circuit, but doesn't show the standard symbols. So I'm wondering what happened to our other people, our other students. Today only 2 students, not 2, only you are in here so far. Now, most of them are drawn using just a circuit, so I can't find.
Isumi is having power cuts, sir. She might come around 7:20 because only then the power will be restored. She said.
Last time also she had the same time, power cut.
Yes, maybe for their area they cut at this time.
Probably. Too bad, it's the same thing, same time. We are also having a power cut, so I'm actually coming from the laptop.
I'm coming through phone, sir. I don't have a laptop. But anyways, our power cut will be at around 9 o'clock in the night. And we'll get it at 1 a.m. 1:30 a.m.
Oh, 1 a.m.?
Yes, 1 a.m. as in night. Night 9 p.m. to 1 a.m. They'll cut.
Oh, that's just...
Because we are living in petroleum side, no. So they want power
Oh,
throughout the day. So we have a chance. But night we can't resist. We have to stay without power.
that's the issue, right? No, I was wondering. I never heard they give the power cut in that time of the day. Usually they either put it in the evening or in the early night, something like that.
Um, yes, maybe I don't know. But when they cut for us, they don't cut always. When they think when their mood is off, they will cut. So 9 to 1:30 maybe we'll have the power cut. Thank God in a way, sir, because
Yeah, you have completed your most of the work, and then
yeah,
it's
and
now
it's
take
phone also
break
no.
again.
I mean, if I have a PC, it's a different story. But
Hmm.
phone is like all time in use, so we have a hard time if not.
Right. So unfortunately, I can't find the 402 and 7 the circuit symbols. Most of them are just circuits already drawn with just the pin numbers. Right. Anyway, so that is what this small circle means. So that means it's a shorthand notation for a NOT gate. It can be at the output side or the input side. But in your level, it will be in the output side, and it will be mostly only for this AND gate and NAND gate. So this is NAND, and this is the NOR gate. And NAND and NOR gates are also known as the universal gates. Because the universal gate means using these two gates, you can create any other gate. Right? For example, let's say you have an AND gate. I want to use not one, okay? That means using only these IC, only these logic gates, you can create any other logic gate. You might need more than one logic gate from the original one. For example, using the NAND gates, let's try to create a AND gate. So how can you create a AND gate using only NAND gates? You can use more than one NAND gate, okay? Can you think of a way?
Yes, if we use not gate twice, which means we can get the exact gate that we're expecting.
How? I didn't quite follow.
Now, sir, we can now we draw NAND gates once, and then
Is your phone a touch screen?
yes, sir.
Okay, let me give you. Where is that one?
Annotation, right?
Yes, annotation, but I want to check whether now I'm using this Newland
So can you
site.
see now?
Yes, yes. Oh, you have the permission.
Then
That's good. Okay.
okay, like this, and then we can use another NOT gate.
No, not gates. I mentioned that
NAND
only using
only.
NAND gates.
Okay, wait.
Your friend is here. Welcome. We are doing digital electronics.
Yes, sir.
Uh, how is it connected? Now the second NAND gate, the green
No,
one
sir,
has
this
two
is not
inputs.
correct, sir. This is not correct because here we getting another output now.
Another input.
Yeah, another input now.
Yeah. So
So
how are you going to do it? How are you going to fix it?
if we give 1 and 1, we get the answer as 0. We get it as 1. We can give another or 1 or anything. Yes, this is the answer, sir.
You can't put any floating inputs.
We can put,
Floating in the sense this one.
yeah.
What is the value of this one?
If we take it as 1 also, we get the right answer. We can get it as AND gate. If we give it as a 0 also, we can get a AND gate because of we have as in a true answer because we have a not in the between.
Okay, so
I
what do you want
don't,
to put there?
there you should put 1.
Yeah, that's one way of doing it. You can put logic 1 fixed here and do it. But that's the first time I have seen it done like that.
Okay, sir. Sorry.
The usual way of doing it is something like this. Clear annotations. The usual way of doing it is you have the NAND gate.
Mm.
You have another NAND gate.
Mm.
You connect the both inputs
Ah,
and put it like this. Because if you look at the NAND gate, it gets 0, 0, 0, 1, 1, 0, 1, 1. Something like this.
yes.
When you connect it means either it will be this line or either it will be this line.
Okay.
Remember?
Then
They are
yeah,
connected. So if you have a 1, both these input will be 1. So that
one.
means it will be this one. Output
So
will
the
be 0.
answer should be
0,
0.
that means this will be both 0. That will effectively mean this side, so the output will be 1. So if you put 1 here, output will be 0. If you put a 0 here, output will be 1. So it is effectively mimicking a NOT gate.
Yeah.
So two NOT gates cancel out each other and you end up with the AND gate. Right?
Yeah. No, sir. I have a doubt.
Okay, then go ahead.
Sorry, sir. Now, if we proceed with the initial output as 1.
In
Okay, sir.
here or in here?
Yes. No, in the first one.
Here.
Yes.
Then you have to have two inputs, okay?
Yeah.
Okay, what do you want to put the input?
As 1 and 0.
1 and 0, okay?
Then we'll get the output as 1, no.
1 and 0, your output will be from here. Now let's write intermediate values. This is 1 and 0.
Yes.
What
The
is the
green
output
color,
here?
1.
This one? Yes, 1.
Okay. So
Then
then
the output,
the input for the second one will be 1 and 1, no.
yes, 1 and 1.
Okay. If it is an AND gate, that means it is true. But
So 1 and 1 means
AND
it's
gate means
0.
it should be true. So if it is NAND gate means it should be 0, no.
This will be 0, right?
Yes. Ah, yes. Then the AND is completed there, no? And
Yeah, so
function is
1 and 0 inputs. The output is 0.
yes, yes. True, sir. Okay, so now I understood. Sorry.
Okay,
Yes.
right. Another universal gate is the NOR gate. This one. Again, any gate can be made by using one or more NOR gates. This is useful because let's say you have some circuit, you are designing some circuit. You want to have maybe 2 AND gates and 1 OR gate or something. If you are saying off-the-shelf components, ICs, you don't have ICs with different logic gates. Either you have ICs with all the AND gates, 1 AND gate, 2 AND gate, 3 or 4 or 5 or whatever number of AND gates. Or you have IC with 4 NOR gates, 3 NOR gates, 2 NOR gates, or whatever. All the internal components are NOR gates. Or maybe you have IC that has multiple NOT gates. But now your circuit has, let's say, something like this. You would have this one and maybe another NOT one and a AND one. So if you follow the easy path, you have to find different ICs. You have to find one IC to implement this NOR gate. So let's say this is your IC. You should have several NOR gates built into the same IC. Like this, maybe another NOR gate here. So you select one of these NOR gates and use it to implement this part of the circuit. Remaining gates are not used. Similarly, to get the NOT gate, you have to get another IC. You have, let's say, 4 or 5 NOT gates here. You use one of the NOT gates in the IC to implement this. Remaining are not used. Another IC to get the AND gates. If you don't have off-the-shelf IC that has a 1 NOT gate, 1 AND gate, 1 OR gate, those ICs don't exist. You have one or more of the same gate type.
Mm.
So if you have 4 gate types in your circuit, you have to have minimum 4 ICs. But if you get a gate with a no or an AND, maybe you can connect them. So some NAND gates. No, sorry, no gates. My tones are very bad. Something like this. Then you might be able to pull this NOR gate directly from here. But for this second NOT gate, you might be able to connect this IC by connecting the 2 inputs. You effectively converting into a NOT gate. So you don't have to buy another IC to implement the NOT gate. You can use the same IC. Only thing is now you have connected the 2 inputs. And for the OR gate, again, you might be able to use some combination to implement the functionality of the OR gate. So using the same 1 or 2 ICs of the same type, you are able to build a complicated circuit. Right? That's one advantage, especially when it comes to manufacturing. It's easy to manufacture the same type rather than putting lots of different types of ICs. Okay, as homework, I am going to ask you two in the sense the 2 students.
2 students, sir.
Yeah, I think Vijay Sekhar was there. Yes, he's here.
He's here.
ඔව් සර් මං ඉන්නවා.
ඉන්නවා. ඔයාගේ first name එක මොකක්ද?
විදුල.
විදුලද දිදුලද? D ද V ද?
VIDUL.
හරි විදුල. Okay. Now the homework is these 2 are the universal ICs, NAND and the NOR. Using them, implement the rest of the logic gates. So using NAND gate, build an AND gate that we already done. Build an OR gate, NOT gate again we have done. Using the NOR gate, build an AND gate, OR gate, NOT gate, and an AND gate. Okay?
Using either one of these, make all the other 4 gates, right?
Yeah, either one in the sense, think of it as
No,
2
I mean both
different
of them.
questions.
Each
2 different
one.
questions.
Okay.
You have to do the same thing with NAND gate,
And
maybe
NOR
the same thing with the NOR gate.
Okay.
But no mixing and matching. You can't put NAND gate and a NOR gate in the same circuit to build another gate. Either totally NAND, if you're doing the first part,
No.
or complete the NOR gates if you're doing the second part of the question. Is it clear? First part, build all the other logic gates using only NAND. Second part, use all the other logic gates using only the NOR gate.
Mhm.
Right. The third one, exclusive OR. This is a little bit of an interesting gate. As you can see, it actually alternates between zeros and ones. To put it simply, okay, let's say you have a 3 input exclusive OR gate. Then what can you say about the output? How do you know the output?
Sorry, sir.
Okay, let's do the truth table first. I am trying to build a truth table for a this one exclusive. So we have to put another line here. A, B, and Q. Okay, for exclusive OR, what will be the output? When both of them are 0? Can you remember the exclusive OR? XOR gate?
Is it opposite to the NOT gate?
No. For the exclusive OR, you have 0, 1, 1, 0. NOT gate has only one input. Exclusive OR can have 2 or more inputs. Right? So the way you determine is you count the number of ones in your inputs. If it is an odd number, output is 1. If it is an even number, output is a 0. So that way you can calculate it even if you have more than 2 inputs. What should be the output of this one?
This is odd number, no, so we have 1.
Yeah. So if you have 3 inputs, this is how it is calculated. Then you have the exclusive NOR gate, just an ordinary XOR gate with a not add out. And by the way, this is written using this symbol as well. Right? This symbol to give you the Boolean expression.
So in this, we have only OR gates now included.
Which one? Here?
No, so when it comes to exclusive OR, we are only considering the OR gates. Or as in, it can't happen with AND gates, no, sir.
Something like SAND gate.
Yeah, XAND.
XAND. No, I don't think we have never heard of it.
Okay.
Okay.
So
But the thing is, it's actually not related to the O operation that much. I don't know why they put that name there. Maybe they ran out of ideas.
No, sir, because we have the, if you take the truth table, that represent more like OR table, no? Because we have one output, then we have one input, then we have an output as well. But when it comes to both inputs only, we don't have an output, like you said.
Yeah, more like OR gate, but it depends on the way you see it. Yeah, kind of like that. Because you have more ones in the output.
Yeah.
But I would have preferred if they have put a different name and a different symbol, maybe a box or something.
Yeah, I know. So when it comes to N exclusive, as in not exclusive OR, we have the opposite of the output. No, nothing else.
Yeah. Okay. Now I think I have a small issue with this one because usually we don't write it as NXOR. We usually write it as XNOR. Yeah. Well, wherever I have copied this, you have a small issue. The N should be after the X.
XNOR.
This X is actually
exclusive NOR. Exclusive NOR.
Exclusive NOR. This X is actually a short form. It stands for exclusive.
Okay.
Right? So the correct term is exclusive O, but for the short is XO. Exclusive O.
Okay.
Then the opposite will not be not exclusive. It will be exclusive NOR gate. So XNOR. I have to correct this one. Though it's not NXOR. It should be XNOR.
Okay.
This is how you can create some of the circuits using transistors and diodes. These have some very severe limitations because you are only using the passive components. Right? So if you try to connect more than several gates together, they will lack the ability to put up enough voltage. For example, I think Shafa, if you remember, I said there's some kind of correction action in logic gates, right? If the voltage is less, it will try to 4.90 within that tolerance. The output, it will try to treat it as logic 1, right? But if you are just using these kind of simple circuits, it will not happen. Any small voltage drop in the A will be represented in this one as well. Any fluctuation will be come to the output as well. So this is just a very simple way of doing it. In real logics, you have much more complicated one. You have kind of like Schmidt triggers and things like that, that actually put it either 5 or 0. They have active components. This one doesn't have active components. Only this one have active component. Again, it is a very simple circuit, right? Not the actual implementation. Right. Why is it showing this equal
So
sign?
with the previous one, the
This
diode
one?
gate.
Yeah.
Now for in case you're giving us a question, so I'm telling my perspective. If it is the truth table, then we can easily answer. But if it is something like, no, because in this transistor NOT gate is quite complicating, because we give an output, we give an input. If it is a true one, then we are getting the output as 0.
Yeah. Can you think of what configuration this transistor is?
This is common base.
Hmm?
No, common emitter. Common emitter configuration.
Vidula, what do you think? What is
CEC.
this configuration? Vidula, are you there? හිටියේ නේද මේ දරුවා දැන්?
ආගෙන ඉන්නේ.
අහගෙන තින්නේ.
ඔව්
මේ
සර්.
configuration එක මොකද transistor?
තුන්වෙනි එකද?
තුන්වෙනි එක. ඔය එක transistor ඉතින්.
ආ. එක සැරේට ඔළුවට එන්නේ නැහැ.
So common
Higher.
emitter is sir. Because
common emitter, common emitter.
කොමන් එමිටර්. එහෙම කොමන් එමිටර්.
common emitter එකේ එක special characteristic එකක් තියෙනවා. මතකද? phase difference එක කීයද? common emitter එකේ.
එකේ ෆේස් ඩිෆරන්ස් එක.
ශාෆගෙන් අහමු. මතකද කියලා?
so difference as in 0.7.
No, phase difference.
Ah,
Where is it? This one,
is 180.
180.
that means what's the relationship between input and output? When input goes high, what happened to the output?
Will become 0.
Yeah, output goes down.
Yeah, it goes down.
When input goes down, output
Will be higher, very much higher.
very much higher. Okay. So in perspective, what I'm basically saying is, if input is like this, output will be like this. This inverted. This side
Yeah, but
inverted.
okay.
So now think of it working in only saturated and cutoff regions. Then what can you say? Let's say you put a logic kind of level, only cutoff and saturated. This is my input.
Hmm.
Which side will be my output? Will it be the same side?
No,
or
sir.
will it be opposite? In the opposite side, right?
It's opposite.
So when
side.
this is 1, this becomes 0. When it's 0, it becomes 1.
Hmm.
Because
Now
it's 180.
So because of this, the transistor acts in NOT gate.
Yeah. You have to make sure it doesn't work in the linear region. Then what's going to happen is it works in the cutoff and saturated region. So when you put 5 volt here, this becomes short circuit. So this is effectively connected to ground. So this becomes 0. When you put 0 volt here, this becomes the cutoff region. So this is open circuit. So this one is then connected to this 5 volt line. Then output becomes 5 volt. All logic 1. Is it clear now?
Yes, sir.
Right. There are some laws in Boolean algebra. This PowerPoint is in the Google Classroom, right? So I'm not going to ask you to take down all of these things, but most of them things you can kind of like either derive or you might have a gut feeling. For example, associative law of AND operation. So either you can start by adding the last 2 terms or adding the first 2 terms. It will still give you the same result. And same will happen the
So I
AND
can
operation.
see only a one note screen, sir.
Sorry.
Not the
My mistake.
present.
This one. So
Okay.
after this one, we move to this one.
Okay, Boolean.
So these are some of the basic laws. And they are very equal to ordinary algebra. For example, when you're doing the addition, the order doesn't matter. If you only have the addition, okay? When you have multiplication or something, then you have to think whether you're doing the multiplication first or doing the addition. But if you're adding, let's say, a plus b plus c, it doesn't matter whether you add A and B first and add C to the result, or whether you add B and C together and add A to the result, or you do A and C together and then add B, whatever the order, it doesn't matter. You get the same result. That is called associativity. Same is true for Boolean algebra. So if you have a logic operation like this, it doesn't matter. Order doesn't matter. So if you have two OR gates feeding output of one gate into the other one, the order doesn't matter. Same goes for the AND operation. And you can see there are some few more.
So also for associativity, the order doesn't matter, no?
Sorry?
Associativity thing, you don't need the order. Order doesn't bother, right?
Yes.
The order, as in earlier what we studied, we had to focus on the order, no? Like
Yes.
A bar dot B.
Exactly. So if you have
For
only,
this, we don't have to.
yeah, if you are in this order, you don't have to worry about it. This you might have to remember distributive, how you can expand while without simplifying the parentheses. So x dot y plus z can be written as x dot y plus x dot dz. Again, quite similar to ordinary algebra, right? This one you might have done something similar in the ordinary algebra. This one probably I don't have to explain, right? X plus 0 is x, x dot 1 is x, x dot 0, right? These are monotone loads. And these are some other things. Again, I don't think you have to think. One important thing is we are thinking about logics, okay? So x plus x doesn't become 2x. It is still x.
Mm.
So although I say x plus x, it should ideally be say true or true. This is still true.
So X is true. Y is 0. False.
I only said part of it. Or false plus false is still false.
Okay.
Right?
Mm.
So if you apply the operation or operation to or operation or AND operation to the same thing, we still get the same output. Right? So don't put 2x here because x is not a number. It is either true or false. You don't have twice the true or twice the false, half a true. Those things doesn't exist. Either true or false. So you have a either true or false value here, true or false value here, another true or false value here. Adding two true values doesn't make you twice the true. Still a true.
Mm.
And this is the absorption law. This one I don't know whether this one you may not feel like your gut feeling. What do you think about this one? Absorption law?
The absorption law is right, no, sir, because x plus y, we have true plus false will give anyways true, no, if it is OR gate.
Yeah, in a way you can think of it
True
like
into true, that is true and true will obviously give us true, no?
yeah,
And no.
yeah. In a way, you're right. That's one way of understanding. It says x dot x plus y is equal to x. It basically says you don't care about the y. It's like a
Yeah.
don't care condition. Right? One way of you can, in a way, the Shafa said, in one way, you can think about what will happen to x. For example, if x is 1, this become 1, 1 plus y, well, it doesn't matter. It will be 1, so 1 dot 1 will become 1. If it is 0, you don't care about this part because 0 times anything is 0. So
0 plus 1
is 1, but you still have to multiply by 0. Output will be 0. So when x is 0, output is 0. When x is 1, output is 1. It doesn't depend on the y. That's one way of thinking. Another way you can simplify it further, x dot x, not x dot y, right? X dot x, what you can say?
if it is 1, it's 1.
No, you can simplify it. X dot x is equal to x, right?
Yeah. Plus
Is it okay? Are you following, everyone?
Yes.
Isumi is
sir.
also there. Isumi, we are doing digital electronics today. I will upload the recording.
Okay.
Then I can do something little tricky. I can take, you can do this one.
So can we bring a third party in, as in like one?
I'm not taking the third party. I'm just removing
One
the
is
X as the common term. Do you see X is here?
okay.
X is here.
Mhm.
I'm taking the X out. Or you can think of it
Mhm.
like this. If you simplify it further, you will get this one. X into 1
Mhm.
is X. X into Y is XY. Can you remember there was a rule something like this? A into B plus C is equal to AB plus AC.
Yes, sir.
Same thing I'm doing here.
Binomial.
I'm starting from here and moving to this direction.
Okay.
Now 1 plus Y, what do you can say about 1 plus Y?
1 plus y is 1, no?
1. X
Yes.
into 1?
A is also 1, no?
X into 1?
X into 1 is x.
X into 1 is X. Otherwise,
Oh.
if you say it's 1, what will happen if X is 0? Right? So X into 1 is X.
Yes.
So we start with this particular expression and end up with this one. Right? So that's another way of doing it, but it's, you may not have that gut feeling when you do it like this. It's a mathematical way, or you can think a little bit and come up with the same idea. So that is the first rule of absorption. Then we have another rule of absorption. This one again, I will leave it for you to show. X plus x dot y is equal to x. I will let it for you to show. Complements. So if you multiply a statement by the inversion of its statement, you will always end up with a 0. So you're basically saying x and not x. So both of them can't be true at any time. It will always be 0.
So it is inverse, no? As in not x, no, that is.
This basically says x and x not x.
Yes. No, so that x was not x is not quite visible enough.
Yeah. There's a bar,
Because
okay?
the bar.
Yeah, there's a small bar there, and there's another small bar here.
Okay.
I'm not sure
No.
what happened there. Maybe some typing issue. So if you have x or not x, it will always be a 1 or a true. That makes sense. Either it is your home, or it is your birthday, or not your birthday. One of them must be true. Last two are very important. These are called De Morgan's law. If you remember at the beginning, I mentioned that when we had the NAND gate, we wrote the Boolean expression as A dot B bar. I mentioned this is not equal to
A bar would be
dot
1.
B bar. There is a way you can convert into that something similar. That is where the Boolean De Morgan's law comes in. So if you have an expression like this, same as this one, put in parentheses, it is equal to A bar plus B bar. You can see the operation here changed. There's another one, A plus B bar is equal to A bar dot B bar. Again, the operation here will change. Right? So these two laws are known as De Morgan's laws. Capital M, because it's a person name. When you are building an exclusive OR using universal gates, you might need to use this one. Maybe you will be able to get out without using them, but maybe you need to use them to make it simple. I don't know, it's up to you. Or maybe you want to build an AND gate, AND gate from the NOR gates, you might be able to use it. Because you can see we are basically changing AND operation to O operations and O operation into AND operations. Right. So for the first homework that I mentioned, to build the universal gate, use the universal gate to build all the other gates, you might need to learn use this particular one. And that is very important even if you are doing simplifications. Because if you sometimes you want to simplify terms within the parentheses, you can use it. Now some exercises. Okay, we'll do it one by one. I'm not I didn't give you enough time to write them down, but I hope you remember all of them. If I am to highlight the most important, some of them you don't need to especially highlight because you already know. For example, x plus y is equal to y plus x, x or y is equal to y or x. It's like a kind of gut feeling. This is a little bit complicated, but still within the ordinary algebra. So in this whole slide, only this one I think is worth taking down a note if you want. The second one, this again will probably come as a gut feeling, believing you don't write 2x here. These two you may need to jot down a little bit, and De Morgan's you may not need to know. Those are the only things that I think you may have to put a little bit of effort into. Other than that, everything should be come natural to you. Right. We'll start the first one.
Can you please show the absorption a little bit? Okay.
Right. Now this is your homework. Not homework, sorry, not homework. Why did I say homework? So next I'm going to ask you to do a little bit of simplifications. Right? So you might be asked to do a simplification or you might be asked to show something. That means the answer is already given. Show that left side is equal to right hand side. So this one is basically for simplification. So we'll start with the first one. Can you give a try? Can someone give a try and come up with the final expression?
Okay, sir.
Isumi, are you there with us? I was, so we were doing the digital projects component. I heard that you didn't have the power. I'm sorry about that. I will upload the this particular recording. But anyway, I believe you were there when we are discussing the Boolean algebra part, right? The last 10 minutes or something. So I believe you can able to do it, right? So give it a try. The first part actually has to do with symbols and truth tables and basic theory and things like that. This one is a little bit independent, so you should be able to do, I believe. So give it a try. Okay. What happened to Vidula? He's gone. Anyway, give it a try, Isumi.
So,
Yeah.
just tell me if it is B.
Let me give a try.
If not, I'll keep trying again.
A bar plus B E plus B.
Is it B, sir?
I'm still doing.
Sorry.
Shafa, is it B or A bar B?
No, so the one before last I got A bar plus B bar bracket into B.
Are you talking about the first question?
Yeah, the first question only. The after simplifying I got it as A bar plus B bar dot B, because A dot B whole thing bar we can write it as A plus A bar plus B bar, no?
Yeah, that one I get it.
So after that I don't know what to do. As in we have A bar plus B bar dot B, no, and then I'm like, I thought I should apply the absorption law. No, sir, I'm
Okay.
sure my gut feeling says I'm wrong.
No, I was just wondering how I can get your answer, share the answer, so I can check what had happened. How can I do it? Is it possible to upload a photo, or you can write in my notepad? Which one do you?
I'll write it then.
Hmm? I don't know whether it's easy for you to draw in this screen.
Is it okay, sir?
Right, fine.
Okay. No, so this is too tight, fatter screen. Okay, so now I found.
Now try drawing. I put a small still life.
Sorry, sir.
Jaffa, I'm not sure whether you will have enough screen to write it.
No, sir, I don't have enough screen because this is so fat.
Can you see the toolbar? Now I change it to smaller line, but then only my lines are smaller, not yours.
Yes, sir.
In
Mine
under
is
that,
not getting small.
there's an
Mine is
option
not.
called draw. Can you see there's an option called draw?
Line width is there.
Yeah, I think you are using the larger.
Okay, sir, now okay. Now okay.
Yeah, this is the small one. And it doesn't matter if you write even over my PowerPoint slide, because probably Ismi had already written down the question.
Okay, sir. After that, I got it like this. Final, the one before the final one. And then I thought absorption law is there, no? X
Yeah, if you got it
into,
like that, then you will only end up with A bar, sorry.
is it that? So until this mine is correct, no, sir?
I'm not sure. I didn't see the first few lines. Can you go
Ah,
it from
then
the
okay.
beginning?
Yes, sir. Then
You
I
can
like
start
that.
from somewhere top here. Doesn't matter.
Okay. Plus B. Okay. And then this is like this. And
Yeah,
then
definitely correct.
and then
Put the
okay.
parenthesis.
A plus B. Okay. And then the after that coming was B. I solved it. That is not without that is not the bracket.
So what happened to this second part? This part?
Yes, wait, sir. That one only. A second part is A bar plus B, no.
Are you still keeping it
And
like
then
that?
B plus B is only I have solved in the first line.
Right. So what happened to
Okay.
bar in here to here? How did you remove that bar?
I didn't remove.
Then there should be a bar right here.
Then mine is wrong.
No, I mean, this is the same expression, right? A bar plus B bar.
Yes.
That is correct. That is De Morgan's law. But when
Yeah.
you're moving from here to here, I think you have forgotten the bar, put the bar.
Yes. Then.
This is the same expression, right?
Yes, sir. Same expression, but I didn't solve the second one. No, I just put it like that. I solved the third one. That is B plus B is of course B, no.
Yeah, that will be B.
Yes.
So
So
although
I
you say
solved the
third
third
one,
one.
it's a single question, okay? All these three terms are in the same expression.
Okay, so then. And then only what I did was
Okay. So this is just a single expression.
yes.
So what
Okay.
you can do is you have multiplication here, right? Why didn't
Yes.
you try to use the multiplication issue?
I did.
You know, when you have something like A into B plus C,
So
you
the
can
screen
simplify it like AB plus AC. Similarly, you can multiply them, or you can multiply this by this one. I don't know. Or you can multiply this and this. There are so many things you can do. Isumi, what about you? Isumi, ivarada? Palaveniyaka?
It's a bit complicated.
It's a bit complicated. Ayyo, right. Then shall maybe I will start.
Make it answer then we'll
Because I'm not value. That will be easy, right? Then
yeah,
you will get the idea.
Yeah, then we'll do the rest of the 5 things and send you.
That's good. That's good. I also thought because this is the first one. So we'll start with something like this. So this is the first part. The question given is A not A plus A dot B bar not equal again. Why am I putting wrong things here? A bar plus B plus B. This is the question, right?
Yes,
right? Then this one I can put something like this.
Yeah, I put that one.
Now I'm doing it in one step at a time, but in reality, you can simplify more than one term at a given line. Right? So this is because De Morgan's, right? Then I can repeat the same thing. And instead of this, I can write B. Why? B plus B is equal to B. Then we can multiply these. Now you have 3 multiplications. So I feel like I will multiply this by this. You can multiply any other 2 terms, you will still get the same answer.
I did the third and second.
Yeah, you will still get the same answer. But the reason I'm doing is it will make it easier, a little bit, not easier, shorter. Let me tell you why. So if I multiply by like this, you will end up with A bar dot B plus B bar dot B, right? A bar plus B. So this term is here. I multiply this expression by B. Are you okay with this one? Are you okay with this particular part? This part, are you okay? මේක පැහැදිලිද එතනට උනේ මොකද්ද කියලා?
ඔව් සර්. සර් මේ හරි හරි. ඔය කිව්වනේ කමක් මට third and second මම multiply කරද්දී
ඔව්.
මට
මේකයි
ආවා
කිව්වේ.
B. මම ඇවිල්ලා B කියලා ගත්තා සර්. ඒකත් මම ගත්තේ D මොගන් නිසා.
කොයිකද डी මෝගන් වලින් මල්ටිප්ලයි කළේ?
නෑ D මොගන් නෙමෙයි absorption කරලා. ඒ කියන්නේ
මේ
second
දෙකද?
term, second and the third.
පුළුවන්. පුළුවන්.
ඒක
පුළුවන්.
absorption කරලා මම ගත්ත B කියලා අන්තිමට
ඔව්
answer.
එහෙමත් පුළුවන්. අපි මේ පාත් එකෙත් යන් ඊළඟට. එතකොට මෙතන absorb කළොත් ඔයාලට එන්නේ
ආ
a plus b නෑ a plus b by එක එහෙමම තියෙනවා. එතකොට මේ කෙලීම ඩොග් ගාලා b වලට සුළු වෙනවා. හරි නේද?
right.
මේ පාත් එකෙත් යන්න පුළුවන්. මේ පාත් එක මීටත් වඩා කොට වෙන්න ඉඩ තියෙනවා. මට හිතෙනවා ඊටට කොට වෙයි කියලා. So what will happen to this one? b bar dot b.
B bar dot B is 0.
0. So I'm not going to writing it, right? This will be 0. A bar plus b. Then I can say a bar into a bar plus b plus, sorry, wrong thing. Not a bar dot b. A bar dot b into a bar plus a bar dot b into b. Right? I am just multiplying this by these two terms. So this one, a bar into a bar become a bar. Right? A bar into a bar into b is equal to a bar dot b. This one again become a bar dot bb. So that again becomes a bar dot b. Right? B multiplied by b is b. So you end up with a bar dot b plus a bar dot b, you end up with a bar dot b. And Shafa, your method I think is a little bit shorter.
Yes.
Right? So we'll start from here. Let me try to draw it using a different color. That way your answer will be, can be read different. So here, using the absorption law, you will end up with a bar plus b bar into b. Right? This is the one I think you got.
Yes, sir.
So what happened when you multiply by b?
Then I got B.
How did you get a b?
No,
b
sir.
into
What
a
do you-
bar, right? This is that one. B into b bar, this is this one. So a bar into ab, you can't simplify it further. B bar into b, this will be 0.
But in absorption, they have told that x plus y is equal to x. No, that's that I took it as B. I was wrong, sir. Then I was wrong again, though I chose the shortest method.
No, okay, my mistake. This is not a bar. This one goes as a bar plus b, right?
Yeah, A bar plus B, whole thing dot B.
A bar plus b, whole thing b. Okay, right, I got it. I'm thinking two things at the same time. So let me clean this and write this particular expression again at the top. So what we have here is a bar plus b bar, a bar plus b into b. Right? Then you put these two terms together and get the absorption law, right?
Yes.
Right. So this term should be still there.
Yeah, that is still there.
So instead of this, what did you get?
B. I
B.
put it as B. Is it wrong,
Right.
sir?
No, it is correct. It is still B.
Ah, then okay.
After this is the problem. Then what did you
Despite
do?
bar, because even though we have bar, we have to put like that, no, sir. ඒ කියන්නේ අර දැන් එහෙ දීලා absorption එකේ දීලා තිබ්බේ x dot x plus y is equal to x කියලානේ. එහෙ
Oh,
වල කවුරුත් bar දාලා තිබ්බේ නෑනේ. Yes.
මේකනේ?
This
Okay.
is only absorption, no. Now in this we have bar also, no, sir. But still we can take it like absorption, no,
Yeah,
without
yes,
any
yes, no issue.
confusion.
X can be
Okay.
anything. It doesn't even have to be a single term.
Okay,
If
okay,
you
sir.
have
Then I
some
understand.
expression here
And then after that,
multiplied by same expression
uh-huh.
at some whatever the thing, this can be another expression, then you end up with this, still this original expression. So this X can be anything. It can be A, it can
Anything.
be A
Okay.
bar,
Okay.
or it can be even something like A plus B bar plus C, D something. As long as everywhere X is this particular term, it's okay.
Okay, sir.
So your absorption
Then
looks perfectly
then
okay.
and then I yes.
There's nothing wrong with
And then
that part.
no, and then again I applied absorption because this looked like absorption again.
Ah, no,
Because
remember. No. Then you can't. Remember, this and this should be same.
yeah, same. I forgot that
It
part
doesn't
because
say
it's
X
B
bar.
bar. Yes, yes.
That's where
And
you
then
had got wrong.
yes.
What you can do is you can simply multiply it. B into A bar,
Yeah. Then
B
A
into B bar.
bar dot B plus B into B bar. That is
You
0.
zero on it. So you end up with A bar dot B.
Yes. A bar dot B is the answer.
Yeah, the same thing.
Great, sir.
So a mistake was not actually in logic. It's basically, I think,
The
small misunderstanding in the theory, or
yeah,
maybe you didn't look at
missing
it
out the
carefully.
bar, missing out the bar.
Right. Try the next one. Izumi, is it okay with you? I did not ask whether you had finished it. Is it clear for you? You are not sure. Okay, in the Google Classroom, you have that PowerPoint uploaded. So go to that slide, I think 96, 97 or something. You have all that laws, right? So when you have free time, go through them and do some questions. Then I think it will be okay. And you try to do it whatever the way you like. Because you know how to multiply using Boolean algebra, how to simplify terms. Go as far as you can, then you will get more practice.
Okay.
The third one is easy. The second one is quite hard.
Second one is easy, especially if you use the method that you use early. You find it hard.
I use a distributivity and then I stopped at the second step itself. But third one I finished.
Yeah, third one is straightforward. 2 lines.
Because it
Second
has only
one,
2 unknowns now. In this we have 3 unknowns now. So it's like
try using the absorption law again. Your favorite one.
okay,
Yeah.
sir.
I think there's a problem with numbering. So the second one, it always marked as one. So the second one, try using the absorption.
Okay. So is it by any chance A dot B bar into A plus C?
Which one is that? Second one?
Second one. Yeah.
No, it is just A.
What is that?
A only.
Only A?
Hmm.
How so?
How? Isabel, what about you? Okay, the question goes as like this, right? So if you are to apply absorption law, where can you see it? Where can you see the absorption law?
The first term.
Okay, what is the result of the first term there?
A.
A. Second term goes as like this. Then you have two A's. So what can you do?
Uh,
You can take the common term out.
Yes. Oh yeah, that is there. The problem is for the second step I took distributivity now. So anyways, I got this term as a
But
third
even
one.
again, then you should be able
Yeah,
to
same,
end up with
the
something
same.
like this.
Yes, I got that.
So
And then
even if you distribute it, you will have something like 1 plus, right? What
yes,
happened to this one?
that is done. And then what do we do? So
1
a
plus something. What is 1 plus something?
1 plus something is 1. My God, I forgot. Perfect, sir. No, because I have forgotten that one. I have taken it as a bracket b bar plus c, and then I got it as a dot b bar and a plus c.
What to do?
My God.
Okay, now let's do the last one. Last one. The one here.
Okay, sir.
Third one. That means the last one. Then I will go to the move to the next session.
Mhm.
Sometimes the questions I give
So
can
is
be
it
very simple
0?
ones, but you can make it complicated as much as you like.
So is it 0?
Yeah, it's 0.
Perfect.
How many lines did you have to write?
Only one line, sir.
Okay, then fine.
One line, but then the second one also I took it as like, second term also 0. So I
Yeah,
finished
it's
it in one
again
line.
obvious, right? Yeah, but if you didn't see it, what's going to happen is you will write, I don't know how many lines you're going to write. But eventually you will end up with 0 because it's just a simplification. But take a very good look at the expressions or even the questions I give you before you jump into it, right? That way you might be able to find some shortcuts or have some idea, right? We'll move to the next main topic. Write the Boolean output of the following right. This should be very straightforward.
I have only one doubt, sir, regarding the last question. Like, no matter what, if it is an and operation, then we have to make it simple as possible. No, like there's no order when it comes to and, right? No, as in, sir, I
I
don't know
didn't
if you
quite follow
understand.
you.
Yes, sir. No, because in this they have given as a dot b c c d and then dot a bar and then they have given plus a, no. So if
Mhm.
anyone is to attempt this question, can they like think of solving a plus a bar? No, right?
No, they can't.
Yeah, because it's all
Order is
record
important.
odd
First,
days.
you have to go with the dot.
Mhm. Okay, sir. Thank you.
Right. We will do the first 1A. 1A. Can you write the Boolean expression for the 1A? Isumi, I hope you remember or you know the basic Boolean expressions. If not, I can quickly give you some quick recap. If you have an AND gate, it will be A dot B. If it is an OR gate, it will be A plus B. Whenever you have a not operator at the end, that means whenever you have that little circle, the whole expression become a bar. So if you have a NAND gate, something like this, A dot B, but whole thing, you have a larger bar, very large bar, A dot B, whole thing, bar. So what you have to do is you have to step by step write the Boolean expression. So write the Boolean expression for here, write another Boolean expression for here, apply this O operation and write the Boolean expression here.
So I'm done.
Okay, what is the expression?
A dot B whole thing bar plus A plus B whole thing bar.
Right. Since so we might have not captured the beginning, so let me quickly go through it. So A, B, you have NOR gate and O gate. These are just connected like this. Okay. So this one is again A and B. If they are connected like this. So this become A dot B whole thing bar. This become A plus B bar. So after here you have A dot B bar plus A plus B bar. So the question doesn't ask you to simplify it, so you can leave it like this. Right? So the answer is A dot B bar plus A plus B bar. Right? Now we'll move to the third question. Before moving to third question, I think I need to give you a little bit of idea of how to convert between these three systems. I mentioned there are three main different ways of writing the logics. Either you can use a logic circuit using gates, or you can write a truth table, or you can write a Boolean expression. You can interchange them using different ways. So first we'll look at how to write a circuit to Boolean expression. You already have done it, so it's not that complicated. So you start with this term, and each time you go across the logic gate, you apply that operation. So at the end, you may have a term like this. What about the other one, Boolean to logic circuit? So in the Boolean to logic circuit, you have to determine the number of inputs. So that means how many variables you have. Do you have only X, or maybe X and Y as inputs, X, Y, and Z? I don't know, whatever the inputs. And negation is replaced by not. AND operation is replaced by AND gate, and O operation is replaced by O gate. Remember the precedence. So when you have a parenthesis, you should start from there. So let's say you have a Boolean expression like this, X bar dot X plus Y. So we'll start with
X plus Y.
plus Y. Yeah. So this is X plus Y. Surely you can see it. Okay, when you zoom in, the animation goes out. Why is that? Let's put it in full screen mode. Right, x plus y, and then you apply this AND operation to make the connection. Well, something has happened when I put it in the window mode. So this is the x bar. Somehow it is shifted. Let's see what had happened. Right. So this is how you do it. So think of it like solving a mathematical expression. You do one step at a time. At the end, you connect them one by one to get the final result. Circuit to truth table, that is very easy. You apply different inputs. Let's say this is the circuit. You have only two inputs. That means there are only 4 possible combinations. As I mentioned, you write it in the incrementing order, 0, 0 up to 1, 1. So when it is 0, 0, you can go across the logic circuit. Okay, this is 0. So if this is 0, this is not gate. So output should be 1. This is 0, directly connected to this one. So this one should be 0. Okay, now you have 1 here and a 0 here. This is an OR gate. 1 or 0 means 1. 0, 0, this is 1. Next step, you apply x0, y1. Okay, x is 0, y is 1. Follow the same step. Okay, this one become 1, this become 1, 1 or 1 become 1. Put the 1. Next is 1, 0, 1, 0, go across the circuit like this, and you end up here. So this is how you can directly convert circuit into truth table. This is the one that most of the time we need to do. Truth table to Boolean expression. Why is that? Logic circuits most of the time try to solve practical problems. So practical problems doesn't come in the Boolean expressions. Practical problems come in a way of vague language-based descriptions, right? Your friend might come and say, okay, I want to have a circuit so that one of my windows is open at the middle of the night, the alarm should sound. Right? So it's not a logic expression, it's not a Boolean expression, it's a description. Or a manufacturing firm might say, okay, when the weight is, or let's say some kind of jam manufacturing company, they might say, okay, if fruit is too ripe, put it into category A. If it's too ripe and small, put it in the dumpster. If it is if it is red and I don't know, weight this amount of gram, put it into B category. If it put in heavier than 200 grams and is green, put it in the jam category, something like that. So you can see it's basically a verbal description. And let's say you are asked to design a robot or something to do that. It look at the weight of this particular fruit, less than 200, more than 200, maybe the color, red or green, and maybe some other factors, and decide what to do. So your robot need to be programmed. Let's say not programmed, you have to build a logic circuit. If you try to go directly from description to logic circuit, it's very, very hard. It's almost impossible. So the usual way you do it is something like this. You have your vague problem description, some kind of verbal description. Then you convert into something that is much more logical. How do you do it? You start with the truth table. You can put a table saying, okay.
So we have verbal description in the exams, no, right?
You might get a very small one. That's why I'm giving you this.
Okay.
Then you can say, okay, what is the color of this fruit, weight of the fruit, what's the action of the robot? Then you can say, okay, color is red, weight is less than 200, whatever. Put something like this. And maybe optionally, you might have to convert them into logical values, but usually sensors, digital sensors will give you 0 or 1. You might have a color sensor, which output 0 if it is green, which output 1 when it is red or something like that. So these terms you might put as ones or zeros. You are converting your verbal description into a truth table. That is kind of easy. You know, in the IQ questions, they have something similar. They give a description. Amal is wearing a hat. The person who's sitting next to the Amal is wearing a green shirt. And I don't know. The scientist is not Amal, neither Kamal. Amal is talking with Kamal. And you have to ask, okay, what's the name of the Amal? What's the job of the Amal? Or who's sitting in front of that or something like that? Then you read through
Amal is taller than Kamal. Kamal is shorter than this fellow.
Yeah, something like that.
Yeah.
Then sometimes you have to put it into some kind of ordered one, maybe in a table or something. That way you can sort it out. You put it in a truth table. Then from the truth table, you come up with a Boolean expression. Something like q equal to x bar plus y, something. Optionally, you can simplify it. You can try to simplify it, maybe x plus y or something. Okay.
And then draw the gate.
And right? Once you simplify it, then you draw the logic circuit. Something like this, then you build it. Otherwise, if you try to read this verbal description and then try to draw this circuit,
it's hard.
It's hard. Because from the verbal description, you will have no idea what the logic is to use. But from the verbal description, you can build a table. From the table, you can give the Boolean, and from the Boolean, you can get the circuit. So that's why this step is important, because I'm now telling you how to convert truth table into Boolean expression. Verbal to Boolean, I can't teach you. It's your common sense and general knowledge.
Okay.
Right? Truth table to Boolean, I can teach you. Simplifying Boolean table, I already told you. Truth table, Boolean to circuit, again, I did it in a very simplified manner. It's not hard, so it should be straightforward. So let me look at this one. So you have this particular truth table. So X, Y, and Z are the input, Q is the output. It's a 3-input circuit. Right? This particular circuit has 3 input, and you need to have 1 output. That we know so far. What's inside the circuit, we don't know. But there are 3 lines going into it, 1 line coming out. First step, select whatever the rows that have output as 1. You have output as 1 here, 1 here, 1 here. So select them. I mark them in red. Then for each of these rows, I am going to create something called minterms. How we are going to do it? Now my inputs are X, Y, and Z. So first I write them as X dot Y dot Z. But only for the rows that we had previously selected. That means output is equal to 1. X dot Y dot Z. Then I look at carefully, okay, whether they are zeros or ones. If any of the inputs are 0, you put a bar. If it's a 1, you don't do anything, you just leave it as there. So I can see there's a row with output 1, so I have to write a minterm for this one. Input X is a 0, so I put a bar. Y is a 1, I don't put a bar. Z is a 0, I put a bar. So the first minterm is X bar dot Y dot Z bar. Okay. Second one. Okay, here's another output where where output is equal to 1. X is 1, no bar. But now Y is a 0, so Y needs to have a bar. Z is a 1. We simply put it at Z. Same goes for the third line. So number of minterms should equal to number of ones in the output. We have 3 rows where output is equal to 1, we have 1 for each. That means you have 3 min terms. Last part, you combine all the min terms using O operator. We had 3 min terms. First min term plus, second min term plus, third min term. So this is your Boolean expression. If you need to simplify it, you can. Maybe you can simplify it. I don't know. Some expressions it's possible to simplify. Some expressions are already in their best way.
Sir, all of
Yes.
a sudden something happened. My Zoom meeting went off.
Are you back there now?
Now okay, now clearly visible.
Right. Where did you skip it?
The
Were you able to?
second step, x dot y dot is
Yeah. You take whatever the places where our output is 1, and whenever the input is 0, in those cases you put a bar.
Mm.
So x is a 0, you put a bar. Y is 1, no bar. Z is a 0, you put a bar.
Okay.
You do the same thing for all the selected rows. You can see here, you have a 0 here, so you put a bar.
Mm.
Last step, you connect all the min terms using a O operator. We had 3 min terms. You connect them using O operator. That's the Boolean expression, immediate Boolean expression. It might be your final one, or maybe you will be able to simplify it further to get a simple term. That depends. If you are just asked to write a Boolean expression, you can just write it. So that's how you can get it. Sometimes you can have multiple outputs. That can happen. That means you have 2 things. Maybe you have a motor and a bulb. You need to control both motor and the bulb. So that means depending on your input, you need to control 2 outputs. Well, basically it's the same thing. You can consider it as 2 truth tables, 1 for each output. So this is 1 truth table. This is another truth table. So for this you repeat this one. For this you repeat the same thing. So now you have 2 Boolean expressions. So it doesn't matter how many outputs you have. You follow the same step. Only difference is for each output you will have a separate Boolean expression. And when you are drawing the circuit, you draw 2 circuits independently. One for this one for other one. Only thing is they both share the same input. So X and Y inputs are shared among them. Otherwise, it's the same scenario. Is it okay? Right. Another important thing is when you are doing this, sometimes if you look carefully, there might be some simple patterns. Okay. I can't guarantee, it depends on the questions. Sometimes the only way you can get a Boolean expression is going through this standard method. So this one is guaranteed to give you a result. There might
if
be
it
some
is like
shortcuts.
two inputs means easy, no? Like for an example, if there are only 2 inputs.
Yeah, it will be easier. But
Yeah.
2 inputs, you don't actually need to have a logic, this kind of thing. 2 inputs,
Yeah.
probably you can do it in your head.
Yeah.
Probably. Right? 3 or more, you will have to write it down.
Yeah.
And even with 3 or more inputs, sometimes you can figure out certain patterns. Certain cases you will notice, okay, this input, I don't actually care. Whenever you have this one, you might get this output. So that's another way, but you can't use both them together. That will be problematic. Either you have to go with your gut feeling and try to figure out a pattern, or you have to go with this standard method and come up with the Boolean expression. You can't have part of the expression from the gut feeling, part from the standard method. Either you have to figure out a pattern that match all the rows in the truth table, or either you have to go through the standard one and come up with the expression in the standard way. But that can be a little bit larger than the shortcut if it is possible to find. But whether there will be a shortcut, We don't know. Depend on the question. There might be a pattern. There might be not be a pattern. Right. So let's go back to the question I want to give you. This one, third one. Now for this one, you don't actually need to go through all the steps,
In the
but I like to
confirmation,
give
sir.
you. So this will be the last
Yeah.
exercise for today. Can you see the
In a
third one?
copy machine, right?
Yeah. But just for the sake of practice, try to follow the steps I mentioned. Read through the question.
Oh.
Then understand what are the inputs and the outputs. Write a truth table for those inputs and outputs. That means convert verbal description or textual description into the truth table format. Write a Boolean expression for that truth table. If possible, simplify it.
Okay.
Draw a circuit for that last Boolean expression.
Okay.
So this kind of questions you can expect in the exam, okay? This is not a very hard one. It's like A-level standard kind of one. Isumi, are you there still? Isumi, ඔය දරුවා ඉන්නවද තාම? නැත්නම් එපා වෙලා ගියාද? ඉන්නවනේ. Isumi, ඉන්නවා. Isumi, මේකේ input මොනවද ඔයාලට හිතෙන විදියට? ප්‍රශ්නේ කියපු විදියට? ශාෆා ඔයාට කොහමද input මොනවද ඔයාලට හම්බ වුනේ? Input මොනවද output මොනවද?
PQR.
හරියට හරි. Output එක?
S.
හරියට හරි. කරගෙන යන්න.
Thank you. Sir, just to make sure before drawing the circuit, is it the output goes as 1111 0001? Am I right?
I'm not sure in which order you have put the PQR.
No, sir, because I have put no, sir, in the question they have told whenever there's no paper, as in whenever the P is 0, the S is 1.
Yes, yes.
Or whenever the Q and R is 1, 1, the S is 1.
Yeah, other times it will be 0.
Yeah, so I'm right, I think.
Okay.
I'm done with the Boolean.
Okay, what did you get?
It's only the Boolean expression, shall I tell? Or should I simplify?
Probably best try to simplify it, right?
Thank you. One, 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 one. If you are to So is it P dash plus PQR?
Almost there. P
Or can I
dash.
simplify even more?
There is one possibility, one small improvement.
Mhm.
Do you rewrite P for the second term?
No, sir, I can't get rid of P. P is coming no throughout. Like it's taking no. Ah, sir. No, wait. Sorry, sir. QR. Q dot R, sir.
Ah, yeah, then okay, that's the final one. Shall I share the drawing facility?
Yes, sir. I drew.
Oh, you already have done?
Yes, sir. It's a small AND gate, no.
Only the AND gate? I thought this was your expression, right? This one?
I was wrong.
Why?
So maybe I can show it like this, no?
Sure. How did you do that P bar plus P dot QR to QR? That one?
This is wrong, no, sir. That's it.
Yeah, P bar plus. Yeah, you can't do that one.
Sorry, sir. Sorry. Until this, is it right, sir?
Yes, until that it's correct.
Okay. Then after that only I am stucking.
Even if you write it like that, I think only one step is there. So can you draw a circuit for that one?
Yes, sir. I can draw for that.
Okay.
R is on and then gate. Both of this will become yes, sir.
Okay, you have
Sir?
PR or
For this, yeah, PQR and P is becoming not and then O.
all right, fine, very good.
And then, but if we can simplify, sir, what am I missing out in here? I want to know that.
You don't actually
Is
need
it
to have P in the second term.
how to get rid of P, sir? Because until I saw this fellow was keep on coming, you know, like
Okay, I can give you a hint. When P is 0, which term it depends on?
it depends. P is 0.
Yeah.
It depends on Q or no.
No, when P is 0, P bar become 1.
Ah, yeah.
Then whatever after that P dot QR, it doesn't matter. 1 plus whatever is 1, right?
So how do we know that P is 0?
No, there are two possible cases. I'm looking at
Yeah,
case
yeah,
by
yeah.
case.
Yeah.
Because there are in mathematics there are several different ways you can do it. So I'm giving you another tool. One way
Mhm.
of proving something is breaking into smaller cases and prove something for all of those cases. Right?
Mhm.
So for the P, there are only two cases. Either it can be 0 or it can be 1.
Mhm.
Right? You have followed the same method when you are describing that absorption law. Whether you,
Yes.
I don't know, novel law, in novel, you have done it. So when P is 0, P bar become 1. So the first term is important, but rest of the term you don't care. Right?
Okay.
When P is 1, what's going to happen? First term becomes 0, so it doesn't become important. But in the second term, only QR is there.
Hmm.
So you can see in the second term, the P, the second term, that letter P doesn't play any role at all. When P is actually 0, that whole term get vanished away. So the second term, so the P in the second term has no use. When P is 1, P in the second term again has no use because it's already multiplying only the Q and R.
Yes. But
How do
so
you
it's
actually
quite
do it using Boolean algebra? Okay, I'll let it do as a homework. But remember, there's another way that when you're doing simplifying, sometimes
Okay.
you need to add an extra term without changing the value. What do I mean
Like
by that?
how?
Yeah,
Okay.
let's say you have something like A plus B. If you want, you can do something like this. A plus, we can say A plus A bar times B. Because A plus A bar is 1.
Hmm.
Then you can simplify it further as AB plus A bar B. Now you are adding some extra terms. Can you remember when you are doing quadratic equation when you are small, right? You have something like, I can't remember the exact, something like this.
Yes.
You take half, you plus something, then you minus
Yeah,
something.
5x minus 3x.
Yeah, it's, I don't know whether I should say it's a, at first it seems like magic, right? You add the term and then everything got simplifies. Certain term becomes square, certain term becomes something. You
Hmm.
add something and remove something. Same
Yes,
thing,
yes.
same idea. But unfortunately, it's not very straightforward as the other simplifications because you have to add the term, right? So you can either add it like this or you can add something like this. Right? Because again, you're adding just a 0. No change to the expression. You can try something similar with your expression. There are more than one way to do simplifications. So maybe you can find a way without that. But I have a feeling maybe you will have to do something like that to get rid of the P.
Sir, can you show the screen again?
Sure, go ahead. Were you able to solve it?
No, sir. I'm asking your screen that A plus A
Ah,
bar.
okay. My screen. I thought it's your screen. Sometimes you can add a term like this. You're basically multiplying by 1, and 1 can be written using a different set of terms like A plus A bar. Sometimes you're adding a 0. So again, doesn't make any change into the value, but 0 can be written as something into complement of something. So
But in
case,
here, after we add A plus A bar, we can't solve it as 1 again because it will give no use. So we have to be like,
yeah, then
A
you have to
into
do
B.
something. Maybe you can take a common term with this one and say, okay, I take
Oh,
A 1 plus B plus A bar or something, and like that, then you do something. Maybe you have a bar here. That can also happen. You have A plus B A bar or something. Maybe you can add a bar dot A and take a common A bar out, so you will end up with a B plus A. I'm making things out of my head, so I'm not sure whether you can actually simplify it. But now with these two, you can rearrange the terms, right? Maybe you have a B plus A here earlier. But now you have two B plus A's. So they might get cancelled out each other or something can happen.
Okay.
Okay. So it's a little bit late in the night. So I think it's time to wind up. Do you have any questions regarding today's lecture? Today we start up with the logic gates, use the basics of logic gates, truth tables, converting between Boolean expression, logic gates, and the truth table, how to simplify logic Boolean expressions. most important thing is how to design a circuit when you are provided with some verbal description. That's the most important thing. So anyone want to ask from that?
I have to ask only about the last question, sir, but usually it is the homework.
Yeah,
Like
give it a try.
P bar plus PQ. Yeah, sir, I'll give it a try.
Okay, then we'll wind up for today. Next week again, let's see whether we can cover a little bit, at least half an hour more. If we are free on Saturday, I will inform you a little bit early. Let me see next. It's again possible. Can we have another lecture on Saturday?
From my side, clear, sir.
Okay,
But
so
ask the others.
so let me put it directly into the chat.
Yeah.
Can we have an extra class on next Saturday? Usually people start coming around 6:30, right?
Yes, sir. For some, at 7:30 only they get the power, but for some, 7:30 only power goes.
Then we have another Zoom. Let's say 6:30 to
No,
8.
like Isumi gets the power at 7:20 around, but Viduraya is the power is going at 7:30.
Okay, then we'll stick to 6.
Okay.
Next Saturday is 20. Not 30th, right? Yes.
Yes.
Yeah, today is 24th.
30th.
So next Sunday would be 31st. So that will be right. Okay, then that's it for today. And let's meet on the next week. Probably next week, Saturday and Sunday, we will be able to finish it, this particular course.